All right, we're going to do some more practice with the mean value theorem, and this is some work that the College Board put out that I think is very, very helpful with understanding the mean value theorem. So we learned this yesterday, so recall that the mean value theorem, or the MVT, states that if f of x is continuous on the closed interval from a to b and differentiable on the open interval from a to b, then for at least one value of c in the interval from a to b, f prime of c equals f of b minus f of a over b minus a. In shorter words, other words, at some point in the interval, the instantaneous rate of change is equal to the average rate of change over that interval. So on the front of this, we have some graphs with the domain from 1 to 3. And we're going to explain why the mean value theorem does not apply for any of these functions on that interval. All right, so for 4a, there is a break in the graph. There is a jump discontinuity. And so for the mean value theorem to be applicable, the function must be continuous on that closed interval. So the reason is the function is not continuous on the closed interval from 1 to 3. All right, for B, this one does have the same domain. There is a value for f when x is 1, but it's not connected to the rest of the graph. So this still is not continuous. All right, and then for C, the function is continuous on that interval, on the closed interval. However, the function is not differentiable at when x is 2. Now, when we're talking about differentiable, we're only talking about an open interval. So it's okay if the function is not differentiable at the endpoints of your interval, as long as the function is continuous on that interval. All right. So same directions, but we have different forms here. So instead of having the graph, we have functions in algebraic form, and we're still going to determine if the mean, or we're going to determine why the mean value theorem is not applicable. So it could be the continuous condition, or it could be the differentiable condition. So when we have a piecewise function, to make that determination, we'll start with continuous. All right, so for the function to be continuous, the limit as x approaches 2 from the left of f of x must equal the limit as x approaches 2 from the right of f of x. And to decide that, we'll just take 2 and plug it in to both of the functions. All right, so we do get 0 equals 0. So the function is continuous on that interval. Or we don't even have an interval. It's continuous. Oh yeah, the interval from 1 to 3. All right, and then we'll determine if the function is differentiable on that interval. Okay, so differentiable, we're going to find the derivative of that piecewise function. All right, So the derivative is 2x for all the x's less than 2, and the derivative is 1 for all the x's greater than or equal to 2. So the limit as x approaches 2 from the left of f prime of x needs to equal the limit as x approaches 2 from the right of f prime of x. Now when I put 2 into the derivative, I'm going to get 4 for the left side, and I'm going to get 1 for the right side. And so they don't equal. So that means that f is not differentiable at that point x equals 2. Okay, and so if we're answering the question, we would say f of x is not differentiable on the interval from 1 to 3. Okay, so this next function, we have the cube root function, and cube root functions kind of look like the S. So cube root functions are going to be continuous everywhere. So continuous, we're in good shape. So let's check out about differentiable. All right, so I would start off by rewriting it as f of x equals x, the quantity x minus 2 to the 1/3. And then I would find the derivative by doing the chain rule. So we would start off with the power, and then we would multiply by the derivative of the inside, which is just 1. So f prime of x is going to be equal to 1 over the cube root of x minus 2 squared. All right, so if there's a place on this function where the derivative is undefined, then the derivative is not differentiable there. And there is, because if x is 2, that's going to give you 0 in the denominator. So f is not differentiable at x equals 2. So our reason is the same. F of x is not differentiable on the open interval from 1 to 3. So the reason that that's going to happen is what we would have there would be a vertical tangent line. And so that the derivative, you can't find it right there. All right, and then for the secant, I would probably think about the graph. Now, it's been a while since we graphed the secant graph. But to graph this, if you guys remember, the secant graph is the reciprocal to the cosine graph. And the cosine graph starts up at 1, comes down, and then back up. All right. So for the secant, where the cosine is equal to 0, you have vertical asymptotes. The secant would not be defined there because the reciprocal of 0 is undefined. So this green one is the graph of the secant. All right. Now we're looking between 1 and 3. Now 1 or pi over 2 is like 1.5 something. So 1 would be right here, and then pi is 3.4, so 3 would be right there. So at pi over 2, the function is not continuous. So we would say the reason would be f of x is not continuous on the closed interval from 1 to 3. Okay. And then G is, I kind of like these graphs, and we talked about them lightly, I think, last year, but not, and maybe some this year, but not enough for, I think, for it to be like solid in your head. But 3 cosine of x looks similar to the dashed line we just did. Oops. But it would be graphed. The maximum and minimum points would be at 3 and -3. So it looks something like that. That's not perfect. But whenever you take the absolute value of a graph like this, anything that's graphed below the x-axis basically gets reflected over the x-axis. So this part down here is going to get flipped up like this. So it gets basically marked out. Now because I have fanciness, I can just erase it. That is what the absolute value of 3 cosine of x looks like. And so that function is continuous. However, at these sharp turns, the function would not be differentiable there. So f of x is not differentiable at the open interval from 1 to 3. Because remember, 1 is here, 3 is there, so we have that 1 point in that interval that is the function is not differentiable when x is pi over 2. All right, and then this last example, it asks, does the mean value theorem apply to f on that interval? All right, and so we have this function where we have something raised to the 2/3, and I'm hoping we're getting to the point where we've done enough of these graphs that you know already in your mind know what that looks like. So when something is raised to the 2/3, it kind of looks like the birds flying in the sky, and that point is actually going to be at 3 on this one because we have the horizontal translation, so shifted 3 to the right. All right, so it looks something like that. Now that's not perfect, but that's basically what it looks like. So first, we want to know if the mean value theorem applies on the interval from 1 to 3. So is the function continuous on the interval? Yes. This function is continuous everywhere. So it's continuous on the closed interval. Is the function, well, let's talk about where the function is not differentiable. So the function is not differentiable at x equals 3. Now, but that is okay because that's an endpoint of our interval, and as long as the function is differentiable between the endpoints, you're good. It doesn't have to be differentiable at the endpoint. So we would say yes, f of x is continuous on the closed interval from 1 to 3 and differentiable on the open interval from 1 to 3. Okay. And then for b, this piecewise function, we'll start with continuous by seeing if the limit as x approaches 1 from the left of f of x equals the limit as x approaches 1 from the right of f of x. Right, and we'll just do that by plugging 1 in. Okay, 3 times 1 minus 1 is 2. 1 plus 2 is 3. They obviously are not equal, so we would say no. And that's at an endpoint. 1 is an endpoint, but that still matters. If we're not continuous at the endpoint, then the mean value theorem is not applicable. So we would say f of x is not continuous on the closed interval from 1 to 3. And if it's not continuous, you don't even need to worry about the differentiable part. All right, so now you guys are going to, in class, work on a card sorting activity. And you have to kind of read it very closely. It starts talking about like as x approaches 2 from the left, the derivative approaches infinity. So you have to just be really careful. Like, for example, if we were talking about this one we drew up here, as it might say something like, as x approaches 3 from the left, the derivative approaches negative infinity, because the derivative is getting steeper and steeper and steeper in the negative direction. Right, and then same thing from the right. As x approaches 3 from the right, the derivative is approaching negative infinity positive infinity, because if I drew a little tangent line, it's just getting steeper and steeper and steeper positively. It's not necessarily the direction that you're moving. It's like if you drew a tangent line there, it's super, super steep in the positive direction. The derivative will be approaching positive infinity. So pay attention to when you're matching those to exactly what it says.